Here we are talking about ratios and rates, and really we're going to be focusing mostly on ratios, but rates, it's important to know about at the start here just how they're different from rates. I mean, they've got a lot of things in common, which is why we talk about them at the same time, but there is an important difference. So let's first start out with a definition of a ratio. So a ratio is a relationship between two or more that's a big important word, quantities. And let's add in here expressed without units, because that's an important element of, you'll see when we're dealing with ratios that there's no units when you write a ratio. With exceptions, ratios are expressed in integers. You'll see that there's something called decimal ratios. Most of the time when you're looking for a ratio, you express it in whole numbers, like 1 instead of 1.1, right? No fractions, just whole numbers as parts of it. Now, you'll see here, since the quantities are in the same units, you don't write the units in your ratio. They cancel out. And you say, well, what happens if I have a ratio where they're not in the same units? Then you force them to be the same units, and then you cancel them out. There's another blank here. It says all blank, for example, cats and dogs, are considered to be like quantities. We call these countable things, right? So anything that you wouldn't normally attach regular units to, like you wouldn't say cats milliliters, right? Or if you were talking about the sofa in your house, you wouldn't say sofa meters or something like that. All countable things we can include in ratios and put them in ratios together. We consider them like quantities. You might be saying, well, cats and dogs, I'm pretty sure those are different. That's one of the fundamental things I learned in kindergarten, that cats and dogs are different from each other. You're right, but as far as being like quantities, they are like. So what I said, this is an important word here, like quantities. I keep coming back to it. What do we mean when we say like quantities? Like quantities are things that would use the same type of units when you talk about them. So for example, if you're talking about distances like this here, 3 kilometers and 2 millimeters, these are very different distances, but they are like quantities in that they're both distances. And you can convert their units to each other, right? You could say, well, 3 kilometers is 3,000 meters, which is 3 million millimeters, right? Oops, I ran out of space there, but 3 million millimeters, I could compare that, if I have my units in there, to 2 millimeters. They are like quantities. I could get them to the same units. Likewise, if you have something like 3 days and 9 seconds, these are both quantities of time. So I could convert days into seconds if I wanted to. I could also convert seconds into days. It would be a very small decimal, but it would be possible. That's what we mean by like quantities. 2 units of mass, 2 units of volume, 2 units of distance, 2 units of time, 2 units of money, or 2 countable quantities. All right. Now, when we write ratios, it's important to know that ratios can show up different ways. Usually, the thing that's most identifiable as a ratio is when you use these 2 dots. It's called a colon, right? If you put a colon between 2 numbers like this, you'd say that that is 2 to 3. That's how you'd say it out loud. You'd say the word 2. And in fact, another way to write a ratio is to actually write the word 2 there, 2 to 3. These are the exact same ratio, just written 2 different ways. And the last way, which you'll see when we're doing math with ratios, often we fall back on this one because it's familiar to us from other operations. You can write a ratio as a fraction. A fraction and a ratio are really closely connected together. We'll see that when we have, you notice in this definition up here, it says that you can have more than 2 quantities in a ratio. You can have 3, you can have 4. If you have more than 2, then this way doesn't really work, right? You could have let's say you have a ratio of 2 to 3 to 4. This is a 3-part ratio. We got 3 parts in it. You could also write that like this, 2 to 3, oops, 2 to 3 to, what's wrong with my pencil? It's running out of computer ink. 2 to 3 to 4, but you couldn't really do that effectively with a fraction. So that way doesn't work for more than 2 parts, even though this one's super popular for when we're using just 2 parts. Okay, now I mentioned that we're talking about ratios and rates, and that I wanted to make sure you understood the difference between them. So a rate, if you look at the definition of ratio, maybe you can pick up on what it would be. It's this like quantities thing is a big difference, and also being expressed without units is a big difference. Ratios have like quantities, and you don't include units in them. Notice here these are just pure numbers. It doesn't say 2 to 3 centimeters or anything like that. It's just 2 to 3. It's a pure number, a lot like a scale factor, if you remember that. Now with a rate, we'll see it's different. So a rate is, we could call it a relationship or a comparison between only two, and then like quantities expressed with two different kinds of units. Just did a line break there in case you ran out of space. There we go. Okay, comparison between two like quantities. Again, this is the super important word in this one. Like quantities. There's only two in a rate. Can't have two or more. So just two like quantities expressed with two different kinds of units. So some examples of ratios. Some examples of rates. You deal with rates all the time in your everyday life. Anytime you're talking about speed, you're talking about a rate. Speed is one type of rate. So we could say 100 kilometers an hour, which we usually write like this. You'll see it when we're doing conversions and math on this. We would tend to write it more like this, 100 kilometers as a fraction per hour, and we would emphasize that it's per 1 hour, just to help us remind us how to do the math on that, okay? So this is one example of a rate. Now notice here, this is a unit of distance. This is a unit of time. There's no way you could convert kilometers by saying, well, let me put 6 more zeros on kilometers and it'll give me hours. There's no way you can convert kilometers to time, right? They're two types of units that are incompatible. You can't convert them to each other, right? Another example that you would see pretty often is if somebody has a job and they get paid, let's say $15 per hour, right? That is a rate, right? We got dollars is a unit of money and hours is a unit of time. And you could say, like for example, if I eat 16 sofas per minute, that would be a rate. 16 sofas per 1 minute. That's actually faster than I can eat sofas, so I shouldn't claim I can eat 16 sofas a minute. But here we have a countable object, which is, here we're using sofas as the type of unit for it, and here we have a unit of time. There's no way you can turn these two into each other. So those are three different rate examples there. Notice we always include two different kinds of units. It can be time, volume, distance, money. It can also be mass, which I didn't write in here, but that's one of them, when expressing a rate. Okay, so let's see if we can figure out whether we're dealing with rates or ratios. Actually, forget that. Let's just jump over to getting a ratio out of this question here. So this is on page 27. What is the ratio of the amount of money in 4 nickels to the amount of money in 9 quarters? So 4 nickels to 9 quarters. Okay, so if we want to get a ratio, remember right now we've got all these words in here, we got to get it down to a pure number. The way that'll work is if we can get them to the same units so we can cancel the units out. So the one that naturally jumps out here is going to be money. Let's get them 4 nickels. Each nickel is 5 cents, so this is going to be 20 cents. And then 9 quarters, that's $2.25. I'm going to write it like this, 225 cents. You could do it $2.25, then convert it to cents, but I'm jumping a step, get us straight there. Once you have them in the same units, you can cancel the units out like that. Now you have just pure numbers. Oops, that's one too many twos there. There we go. Whoops, having trouble today with the old tablet. 20 to 225. And we're almost done. We just like with fractions, we want to reduce this to a simplified fraction as much as possible. So we could reduce this to 4 to 45. I'm just dividing both terms in this ratio by 5. 20 divided by 5 gives me 4. 225 divided by 5 gives me 45. So that is my ratio for the amount of money in 4 nickels to the amount of money in 9 quarters. Very important ratios. Notice that the order of the words in the problem that you're being asked has to match the order of the numbers. This number represents the 4 nickels, the amount of money in 4 nickels. This represents the amount of money in 9 quarters. Okay, you couldn't have 45 to 4 as an answer here. That would be wrong because of the way the question is asked. All right, let's do a couple more examples here to get you in the swing of things. Number of days in a week to the number of days in a year. Now, some of you guys will say, well, sir, number of days in a year is actually 365.24. It can be. I know you're right, but I'm just going to go with 365 for the number of days in a year, and then the number of days in a week is 7. And then I see, well, can I reduce this? Can I simplify this just like I would a fraction? 365 isn't divisible by 7. And 7's a prime. So no, that's my final answer right there. Notice there are no units in my answer. 7 days to 365 days, I canceled the days out right away and went straight to the numbers. Amount of time in 1 week to the amount of time in 1 day. I get a lot of people saying, okay, well, let's get that in hours. So they figure out there are 168 hours in 1 week. And then they say the amount of time in 1 day, that'd be 24 hours. Again, technically it's not exactly 24, but we're going to keep it like that. And then they cancel out the units, which is the reason why you get them in the same units to begin with. And then they have this fraction 168 to 24. They will say, just like a fraction, can I reduce that? You can divide both those numbers by 24, which gives you 7 to 1. But then some of the sneakier guys among you might say, well, if instead of expressing time in hours, can't I express time in days? Can't I say like 7 days? Oops, what is wrong with this thing? To 1 day right off the start? Because a day is a unit of time, right? Yeah, you could. You could. 7 days to 1 day, and then you just cancel the units, and you already got 7 to 1 as your answer. That's absolutely a correct answer for that one. So if you were sneaky like that, well done. Good job. The value of a dime to the value of a toonie. So you could say, well, a dime is 10 cents. I know that. A toonie is $2. So 10 cents to $2. Let's get them both in the same units. 10 cents to 200 cents. Now that we have them in the same units, cancel the units, reduce the fraction, and I get 1 to 20 as my answer, just like that. Okay. Here we're seeing some examples where we have more than 2 terms in a ratio, like this one here, value of a quarter to the value of a dime to the value of a loonie. Value of a quarter is 25 cents. Value of a dime, 10 cents. Value of a loonie, $1. All right, let's get them all in the same units to start with. That would be cents. Some of you guys might have already done 100 cents in the first step. That's perfectly good. Once we get them in the same units, cancel the units out, and you have 25 to 10 to 100. Now you're going to simplify this. Now with a 3-part ratio, you look and you say, okay, it's got to be something that is divisible into all 3 parts of the ratio, right? Like we could divide all these by 5. Sorry, let's do that. So right away that would give us 5 to 2 to 20. And at this point you might say, well, I've shrunk it down this much. Do I stop there, or like could I divide both these guys by 2 as well? Or maybe divide both these guys by 5 as well? No. In a 3-part ratio, you only simplify, you only reduce by something that you can divide all 3 of the parts by simultaneously. Otherwise, you stop, and this is actually your final answer, 5 to 2 to 20. Okay.